Hi, everyone. Thank you very much for coming to our talk, and thank you very much to CppCon for having us. My name is Peter Martin. I'm here from Bloomberg. With me is Mike Fairhurst, who's here from GitHub. We're here to talk about a project that we've been collaborating on, and that is validation of C++ contracts with static analysis. Or in other words, can we make use of the contracts features in C++26 to find bugs in programs before they even run? So here's what we plan to cover. I'll give a quick introduction to C++26 contracts and our motivation for the project. Mike will go over some tools and techniques we've been using for static analysis of contracts, and that will include deep dives on two tools, CodeQL and Z3. I'll talk through an initial evaluation we ran using these techniques internally at Bloomberg. And finally, Mike will go over some future plans. And hopefully we'll have some time for questions at the end, but if not, we can take those to the hallway. A quick about me, and I'll let Mike introduce himself when he takes over. As I said, I work at Bloomberg, and specifically in our product security group. And my team specializes in large-scale code analysis. I've been at Bloomberg for about 18 years now, working in various different teams across our engineering, CTO, and CISO departments. And in recent years, I've had a focus on software security. So because we're going to be focusing a fair bit on C++ contracts in this talk, I wanted to start with a bit of background to catch anyone up who may not be aware of this feature. That said, we realize there have been several other talks at this conference on contracts, including excellent talks by Herb Sutter and John Lakos, and so we'll try to keep this section speedy. So what are C++ contracts? The introduction of contracts in C++26 gives us some new language keywords that allow us to specify a contract on a function. These effectively give us a way to encode what we expect to be true at API boundaries, both when a function is called and what can be expected to be true when it returns. So these are intended to help us surface misuse of functions. And specifically, you'll see these pre and post keywords that can be used on function declarations to specify preconditions and postconditions. Preconditions set out the requirements about what must be true for a call to the function to be considered in contract. Postconditions set out what we can expect to be true at the point it returns normally. And finally, contract assert gives us a way to perform contract checks within the body of functions. So just to illustrate this with some examples, here you can see the use of the pre and post keywords. Sorry if it's a little blurry. And you'll see these on the function declarations. So in the case of divide, the contract here is that b cannot be 0, which avoids division by 0. In the case of abs, you'll see the use of the postcondition syntax for naming a return value. So here we name the return value r, and we specify that the return value has to be greater than or equal to 0. There are some other key things to know about contracts, but these are slightly less relevant to our talk, so I'm going to gloss over them in the interest of time. But a key takeaway from this slide is that their behavior is highly configurable. You can decide whether or not checks are even done, or exactly what happens when a contract is violated. And this can be chosen at build time through compiler flags or at runtime. So given the existence of this new language feature, a logical next question is, can we use it to identify cases based on the code alone where calls are being made out of contract? So if feasible, we'd like to find these kinds of bugs as early as possible without even running the program. If we can find these kinds of bugs in a testing phase or in CI/CD processes, that's much nicer than waiting for a contract violation at runtime. Maybe there's a contract violation that's lurking in a rarely hit code path, for example. Or maybe for some reason, contract checks are turned off at runtime. So in these cases, we can still potentially reason about whether their conditions would be met with static analysis. We can't, though, clearly say completely comprehensively whether all contract assertions will be true or false at runtime, because these are Boolean expressions, and in some cases, those can depend on state that will only be knowable at runtime. However, we should be able to reason about this in at least a subset of cases. And if we can do that, hopefully we can catch at least some bugs ahead of time. So we were interested to explore this topic in general. GitHub have a tool for customizable static analysis called CodeQL, and this seemed like it would be a promising building block for analysis like this. So we decided to make this question the subject of a collaboration project. Mike is going to go into more detail on CodeQL and the approach that we used to achieve this. Before I hand over to Mike, though, I just wanted to mention some acknowledgements, because while Mike and I are up here talking, this project has had contributions from several others. And notably, the analysis method we're going to be talking about and the initial POC of it came from John Singleton, now of Microsoft. And several others, both at GitHub and Bloomberg, assisted on this project over time, including Luke Carty from the GitHub side, and from the Bloomberg side, Julian Verneig and Joshua Byrne. Now I'll hand over to Mike to talk through the analysis method.
Hi, everybody. My name is Mike Fairhurst. I work at GitHub. I'm a senior CodeQL analysis engineer in the GitHub Expert Services division. So we work on custom solutions for our customers. My background is in languages and type checking, static analysis. I've previously made a statically typed language with type inference, and I've previously also made a just-in-time compiled language. And that's kind of why CodeQL is so interesting to me. I also have an auto insurance policy, but unfortunately that can't be checked with static analysis. So we'll have to move on to what we can. So if we look at a particular case where we have some function called format hour, this is going to have a contract saying that the hour that we're formatting should be a valid hour, so it should be between 0 and 23. We can clearly see that there will be cases that are trivial to analyze, that this constant value 1 is definitely within the contract, and that this is valid. And we clearly will have cases where the contract is, maybe not likely cases, but in theory, if we see code like this, we can trivially analyze and see that 24 is outside of this range. And we can report an issue here. One thing I would like to note is that just because a code path, just because an invocation of a function clearly violates its contract, doesn't mean that it's never going to happen. It is definitely possible that there is code that is essentially like this in disguise out there in real systems, where a branch is extremely unlikely to be taken, and in that path, a contract will actually always fail. And so this is something where if at a minimum we can find these cases, then we've already done something. But we know that the real world is more complicated than integer constants. So this is an example where we have a command line tool. This executable reads the command line argument, it parses it to an integer, and it calls the format hour function with that integer. If I pose to this room, do we know if this function will violate the contract or not? The real answer is that we don't know. We don't have enough context. Of course, if we deliver this as a command line executable to our users, then we should really expect that eventually someone is going to type in the value 24. And in that case, we would violate the contract. But we don't know where it's being deployed. It could be deployed as an internal tool, being used by another internal tool, where the range of values actually will always be valid. So the answer of whether this will violate the contract is really that we just don't know because we don't have enough context. But nonetheless, I think we would all agree that this is a better version of the previous code. Those of you who have watched the other contracts talks by, for instance, John and Herb, you will have seen that them talking about how contracts are not intended to be a primary workflow. They're not intended to be your primary source of bounds checking. So even if this command line tool is currently deployed to a program that inside of a setting where it will never violate a contract, we probably do want to insert this check in case that changes in the future. And by adding a check like this, static analysis tools can see that we have a check like this, and we can say that we can categorize this differently. And why we would want to catch these things in general. Why would we want an analysis tool to look at all these paths, analyze what values are flowing where and which may violate a contract. Many of us have seen this before, that there have been studies done that show the relative costs of discovering a bug early versus discovering it in production. And it is far, far more expensive to discover a bug in production, whether it's a security vulnerability or a bug your users have stumbled across. And so this is something where we do want to push left. We want to find this bug earlier where it's cheaper, such as in your CI/CD. We can find many of these bugs by turning on contract assertions and by running our program. We may find this via unit tests in our CI/CD. We may find this via fuzz testing in our CI/CD. But it's worth noting that unit tests only explore the interesting possibilities of inputs that we chose to write by hand. And then the fuzz testing can only explore certain paths with likelihood of success. So there will always be branches of the code, possible inputs that do interesting things in your code that a fuzz tester won't find, that your unit tests won't find. And the static analysis is very good at exploring all reachable code, and the static analysis is the right tool to find these cases. So what cases, right? What are the cases that we can try to analyze? There are cases that we can always verify, such as we saw earlier, where it's very trivial to verify. There are cases that require context that we simply don't have. These cases will always be a challenge for these tools. Where we're really interested is in this third case. We wanted to find out how many cases we can infer by applying sufficient deductive reasoning around the code in order to highlight particular places where we believe there's a strong likelihood that a violation is really, truly possible. As a quick note, I will say we're not pursuing formal verification. Formal verification is used in very safety-critical software systems to guarantee correctness. We're not interested in guaranteeing correctness and with all the difficulties that come with that. We're really just interested in finding some bugs. If we can find one bug, that's better than none. So at GitHub, our tool of choice for static analysis is called CodeQL. CodeQL offers default queries for C and C++ and other languages. These cover known security vulnerabilities such as SQL injection, buffer overflow, these kinds of things. We also have some quality queries. Some of the default queries will cover common bugs, but we also have support for coding standards like AutoSAR, Cert C++. I'm also currently working on the MISRA C++ 2023 rule set, and that will be hopefully done soon-ish. We also have support in general with CodeQL to write fully custom queries of whatever you want. And when you're writing a CodeQL query, when we're writing our default queries, this is the sort of information that we have available for our static analysis. We have the type information in your program, so we know all of the classes you've defined, all the structs. We know the types of all of your variables. We know the members of all your classes, etc. We also have the full syntax tree. So we have every operator. We have the operands to every operator. And we also know how you've structured your program in terms of if conditions and loops. Which brings us to the control flow graph. The control flow graph actually knows how code is reachable from which conditions. We can see where your code will loop, where your code will have early exits for a function, and things like that. And then we have the call graph, importantly for analyzing C++. Overload resolution is very, very difficult. It's a complicated algorithm, a complicated process. It doesn't always do what developers might expect, and sometimes it's hidden in things like operator overloading. So when you go to write a query with CodeQL, all of that has been already resolved for you. You know all of the call sites to every function and every operator overload, which is very important. This is overall how CodeQL works. In the upper left, we have your code base, your build system, and your build artifacts. And this is what you already have today. CodeQL adds an extractor. You can barely see the arrows here. I apologize there. CodeQL is an extractor that can observe one of your builds. And when it observes your build, it traces all of the compile flags, as well as all of the compiled files and all the flags in those commands. From that, we can plug in our own system where we extract all of the expressions, all of the statements, everything that basically every fact about your code that we can aggregate, we do aggregate, and we put that into a database. It is a write once, read many times database Once we've created the database, it's finalized and it's read-only. So then you can write queries in the upper right. And your query gets to pull in a bunch of standard libraries that are also written in QL, the query language. And together with your query and the standard libraries, it can be compiled into a highly optimized form in order to run very efficient searches over this database and produce your results. This is what CodeQL looks like in 100 characters or less. At the top line, we have this import CPP. That imports the CodeQL standard modeling of C++ programs. And then we have what looks much like a SQL statement. So we can select function calls and functions. We look over the set of all function calls and the set of all functions, and we correlate the two together so that the function should be the target of the function call. From there, we select the function call and the function, and if you run this in VS Code, you'll see these two columns of results. On the left, we have a clickable link to every function call, and on the right, we have a clickable link to the function that it's calling. But CodeQL isn't just a query language, it's actually a very rich language. And it has standard libraries, and you can write your own libraries. Essentially, CodeQL operates on the facts about your program, and you have the ability to write new facts about your program. These look much like functions. We call them predicates, and they don't return a value, they're just a logical statement. So in this example, we can declare a fact that describes which expressions are negated. It isn't super important that everybody here understands exactly how this works and leaves this talk being able to write CodeQL, but I did want to give an overview of how CodeQL is a rich language. And on that note, it supports object-oriented programming as well, which may seem interesting for a query language to support object-oriented programming. But the way that it works, in essence, is that we use object-oriented programming to constrain the set of types, the set of data that matches something. So here we are able to make a negated expression, which represents the set of all expressions that are negated. This filters down the set to what we want to talk about here, specifically when we're writing code related to negated expressions. And now that we've filtered down this big set into this smaller set, we can actually write behavior, which looks much like member functions. And we can write this behavior that's specific to the constrained set of data. So once again, nobody here is going to be a CodeQL expert just from seeing 100 slides and 100 characters or less of CodeQL plus this. But I wanted to give an overview of how rich CodeQL really is. And it's time to go back to contract specifiers. So contract specifiers, we remember, we have preconditions to constrain the function inputs. We have postconditions to constrain the function results. And then we have contract assertions that are inline in the function body. And we should also talk about what contract specifiers can and cannot do. This is going to deeply affect how we perform our static analysis. One critical safety feature of the way that contracts are designed is that when you refer to a variable inside of a contract, it's going to be constified. It's going to be implicitly const. You will not be able to mutate values that were declared outside of the contract. This is very important because contracts should ideally not have side effects. But there are two things here I want to call out that make static analysis of contracts fairly difficult in some cases. Inside of contracts, you can call functions. You can call functions of arbitrary complexity. You can really do whatever you want inside of a contract. It's incredibly flexible, which is great, but of course, at the limits, creates problem for analysis. On that note, when we're calling functions, we can do all sorts of things. Like we can have side effects, like allocating memory. We should not have side effects that affect our program in any sort of meaningful way that we can't turn these contracts off and get the same essential behavior. But it is possible. And of course, if we're allocating memory, that becomes a difficult thing for static analysis to track how that memory is allocated and mutated and passed around. And you can absolutely have undefined behavior in your contracts. That is absolutely possible as well. Luckily for us, we already give in CodeQL many queries that are aimed at detecting undefined behavior. But if there's undefined behavior we can't detect with those rules, then we are essentially in troublesome waters, and that's just how it works. So this is an example how it might look. So we have a precondition that's invalid here. We take the parameter x and we attempt to increment it inside of the precondition, and that's not allowed because of constification. Next, we have an extremely inadvisable contract that I don't recommend anybody add to their program. We're doing all of the naughty things I described. So we're going to call arbitrarily complicated functions. We're going to allocate memory, and we're going to have undefined behavior as well. Lastly, we have an example of how postconditions also have constification. If this R captures the return value of F, no, we can't change the return value. So with all of the complexity that's allowed in contracts, it really may seem like static analysis tools just aren't applicable here. That this just isn't a problem amenable to static analysis. And we certainly know that there will be contracts out there that are written in this way where that's absolutely true. But we still believe that we want to pursue all of the cases where we know that these additional optional things, these very flexible features such as arbitrary function calls, we know these won't always be used. And so those are the cases we want to explore. And when developing static analysis, there's kind of two camps. On the right here, we have the camp of what formal verification sort of provides. Or sorry, is it on the right? Yeah, it's on the right. So this is where we write a static analysis tool because we want to guarantee that something is correct. This is something where static analysis is very strict. And we might be okay if some of our reports are false positives, where we have reports that don't actually indicate any real problem in the code, because we want to know that if there's no reports, that our code works correctly. Most of us tend to actually live on the left. Most developers really prefer living on the left. Here, we as developers have a lot of jobs we want to do. We really don't want our static analysis tools to be noisy. We really want the static analysis tools to have some trust that I know what I'm doing. And we really want it to be the case that when we get a result, that result is a true positive detection, that it really is a real problem that we need to address. We're okay missing some examples, not finding every bug, but we really just want to make sure that when we do see an alert, that it's a real result that we can address. So our modeling has taken on these three aspects of contracts. So we support integer range analysis. We've taken a look at integer range analysis, where this loop creates an integer that's outside the range of the contract. We also support nullity analysis, tracking which pointers may or may not be null, and we sometimes have assertions that a pointer must be null, sometimes a pointer must not be null. We also have some support as well baked in for object field analysis. So in this example, we have some class or struct C that has a member X. Inside the contract of F, we actually constrain what that member X of the argument should be. And we do have support for identifying a violation such as this one, where inside the body of G, we set X to an invalid value if we're going to pass C into F. So we're going to focus on integer range analysis in this talk. How do we take these particular examples? We have a function on the left and we have a call site on the right. How do we validate this inside of CodeQL? Luckily for us, CodeQL comes with a standard library that has standard predicates for finding the lower bound and the upper bound of an expression in your C++ program. This is an example. This is results from the Linux kernel of what that looks like. And then we can find, in this case, we're going to look at assertions. We can write a predicate such as this that we can use in our queries to find a contract range. So here what we're doing is we're looking for macro invocations where they're named assert. We then check to see that there is a comparison operator that is generated by that macro. And then we check to see that the left-hand side of that comparison operator is an access of the parameter. We then can see what the operator itself is, could be greater than, equal, less than, etc. And then we check on the right side that we have we take the constant value of the right hand, assuming that it's a constant. This is one way that we can write sort of a query, a predicate, to extract information about an assertion of a parameter being within a certain range. But can we handle cases like these? So this is the first example we have here. We're going to assert that the base and the power cannot be null at the same time, or cannot be 0 at the same time. We also have an assertion that if the month is February, the day is to be less than or equal to 28. We've also seen cases of where nullity analysis and integer range analysis are combined into one contract. We've seen that before. And then we have cases where the range of one parameter maybe depends upon the range of another parameter. So in order to solve this problem, we have decided to bring in Z3. You may have heard of Z3 or may not. It is a theorem prover, or you may hear referred to as a constraint solver. It's an open source project by Microsoft with a friendly open source license. It's very fast, and it's designed to optimize logical constraints. Z3 operates on a language called SMT. There are many SMT solvers. Z3 is one of them and one of the most popular. Inside of SMT, we can define, you might think of them as variables. They're constants. We have x and y, and then we constrain x and y with this assertion. We constrain x, we add a constraint that x times x is equal to y times 3. Then we have additional commands that we can use in SMT. We have this command check satisfiability, where we'll check if there's a way to solve this theory, to prove this theory. And then we also have an option to get model. And this actually describes the proof that Z3 has found. So you can see below here we have the Z3 output. It's going to tell us that the theory is satisfied, and it's going to tell us that it thinks that y is 3 and x is -3. This is one solution to those constraints. Here is a real geometry problem that my manager sent out to our team on a Friday for fun about 2 weeks ago. And I thought, well, I gotta solve this with Z3 since I'm working on these slides. So here we have assertions that, well, first of all, we have some setup code and some defining functions and things like that. But importantly, we constrain that the yellow area, as far as we know, is 3, the red area is 2, the green area is 4. We have additional constraints that the total height of the square is the total height of the red area, and that the total width of the square is the width of the red area plus the width of the yellow area, etc. And then we add a constraint that the areas of the red, yellow, blue, green triangles added together must equal the total area. And when we run this with Z3, it instantly finds a solution for us where it tells us that the blue area has an area of 7. And we can see, in addition, the area of the height and width of all of the triangles and the overall square. And you might be asking yourself, well, but if CodeQL is a logical query language that solves logical constraints, and Z3 is a proof solver that takes logical constraints and finds a solution, why would a CodeQL query need to use Z3? And there's really 2 reasons for it. So one is that if we wanted to use the CodeQL engine in order to solve the constraints that were laid out in your contract, we would really need something like eval, or we'd need to have a CodeQL query that generates a CodeQL query that checks your code, or something like that. This isn't possible in CodeQL. But by using Z3, we do have the ability to have a CodeQL query that generates SMT statements, passes that into Z3 to sort of act like an eval step. The other reason why we use Z3 is that Z3 and CodeQL are solving different problems. CodeQL is a query language. If I specify a particular set of constraints, I want to find every solution to those constraints. As opposed to Z3. Z3 is optimized to find one solution or one counterexample. It needs to find some proof, not every proof, or some counterproof. So overall, this leads it to being that Z3 is solving a subset of what CodeQL solves in a certain sense here. And it can just find that one solution a lot faster than CodeQL would find all solutions. So overall, this is our process. We have this function f that specifies a contract, and that gets translated into this SMT. We create a constant named x after the parameter. We define the precondition. There may be more than one precondition. We also then take this call site. We can find inside of G that there's a call to f of y, and we can then take the range of y using standard CodeQL range analysis, and we can generate constraints on top of the parameter x, that it must be within this range. These two blocks of SMT get concatenated together, and then we go into the lower left corner. This is a final section that we add, and we're essentially going to assert a theory that one of the preconditions fails. We want to find an example that would show that the contracts will be asserted, will be violated. So our theory is that someone is going to violate the contract. It is possible to violate the contract. We just don't necessarily know how. So that is why we assert that not all of these succeed. We assert that one fails. When we run this into Z3, it gives us an output like this. It tells us that our contract can fail because the value of x might be 0, which violates the precondition. Overall, this is sort of what we've modeled. Mostly the mathematical concepts because they're easier. We have addition and subtraction, Boolean logic fully supported. Multiplication is slightly harder to do range analysis for, but we have some support for that. Division is not supported well in the standard range analysis, but it is mostly well supported inside of Z3, with the exception of that it will define divided by 0 for you, so you have to be tricky there. And then we have other cases such as bitwise operators where we have support for a lot of what, not perfect support, but we've done mostly what we can to support bitwise operators in range analysis, but we haven't implemented that in Z3 yet. And then we have stuff like function calls, arrays, and derefs that we haven't handled. And with that, I will pass it back to Peter to talk about our evaluation.
Thank you very much, Mike. So Mike has outlined the key elements that we needed for this approach. And to recap, this was our rough plan. So we take a program that we want to analyze, we build a CodeQL database out of it, and then we plan to use the range analysis features, as Mike described, of CodeQL to reason about the possible values that variables can hold at a call site to a function with a contract. We can also, using CodeQL, extract the preconditions, the contract of the function that's being called. And then for each call site, we'll be combining those two things into an SMT formula as input to Z3. And Z3 can tell us whether they're compatible. And if they're not, it can give us a counterexample. So we had seen this approach work on some toy examples, but we were interested to see would it scale to real programs. Something you might be wondering, though, is how can we evaluate this on real programs when C++26 contracts syntax, it's not in popular use yet. So in particular, there's limited compiler support for contracts at this point, and that includes the compiler front end that CodeQL uses when it's building a database out of your code. So we needed some way to test this technique against real code, but where the contracts are not specified using the C++26 syntax. Thankfully, we had an answer to this in the form of BDE. So some of you may be familiar with BDE. It's Bloomberg's set of foundational C++ libraries. And these are open source. You can find them at github.com/Bloomberg/BDE. And the reason I mention BDE is that there are some existing conventions in BDE library code that happen to be quite similar to the contracts features. And this allowed us to test some of the same techniques, but even in the absence of the new language features. So one useful convention in BDE library code is that a rigorous approach has been taken to documentation, and specifically function-level documentation in this case. And one phrase that you'll see in BDE code very commonly is in a comment above a function declaration, and which gets translated to a Doxygen doc, behavior is undefined unless. So this does effectively set out preconditions in human readable form. It's a plain language contract. But yeah, it's human readable. It's not in a form a compiler or static analysis tool will understand. Even more usefully, though, another convention in BDE code is to validate those preconditions at the beginning of function implementations. And this is done using a family of assert macros called BSLS assert. So these assert macros are also provided by BDE. And again, they have some similarity to the C++26 contracts features in that build flags can determine whether or not these asserts are used at runtime. And you also get the flexibility to define custom assert handlers to be invoked when your assertions fail. So for the purposes of our evaluation, we focused on inferring contracts from these BSLS assert statements in function implementations. And we've done this in a way that can be expanded to support the official language syntax in future when that's available. This did, however, present us with a minor logistical challenge. So as I was saying, we wanted to extract contracts from these BSLS assert statements. In a typical program calling into functions in library code, it will only have the headers for the library. It won't have the .cpp files for that library. And CodeQL, when it's building a database from your program, it sees what the compiler would see. So sadly, in our case, it meant that these BSLS assert statements, at least the ones in the .cpp files of the library, are somewhat off the radar for analysis. Incidentally, we won't have this problem with C++26's contracts, because if you remember, pre and post are specified on the function declaration in the header. So in that case, the program under analysis will have the contract in its source code. In the meantime, though, we needed a way to deal with this. So we had a couple of options at our disposal. The first option was, for every program we wanted to analyze, we'd have to run a full dependency build when we're building the database out of it. That is, build the program from source and its library dependencies from source. And that would work, but it would be a little bit awkward. And in particular, it would mean tinkering with the build for every program we wanted to analyze. But secondly, it would be a little bit wasteful in terms of compute. Say there's many programs calling into one library. We'd have to be building that library dependency again and again. So we had the second option, which was to run a one-off analysis of a library that many programs are calling into and summarize its contracts, effectively export those contracts and have them supplied at analysis time when we're analyzing a program that calls into that library. So we ended up going with the second option, which seemed a little bit more flexible. It does add a little bit more complexity to our approach, but we now have this concept of a spec database. And this spec database can contribute at analysis time containing the contracts for a library that the program will be calling into. And if you remember Mike's slides from earlier, he showed CodeQL translating the contract on a function into SMT form. And that's what this spec database holds. So onto our evaluation. We needed to select a target set of functions to extract contracts for. And we decided to trial this on BDE's date functionality in particular. The thought here was that these functions and their contracts would be quite amenable to analysis. And in particular, that's because our grammar was somewhat limited in what it could support. And the thought was these date functions and their contracts would be dealing largely in a subset of grammar that we could support. So in particular, that is simple arithmetical and logical expressions and contracts that deal in numeric and Boolean types. So we used a combination of internal Bloomberg package metadata and source code search to find 6,000 projects that were making calls into BDE's date functions. And of those, we decided to prioritize a set for analysis. So we picked the top 1% of those, and we were going for breadth of functions called here. So we wanted to find a smaller number of databases to analyze, but where we were still covering lots of contracts. And after restricting to the grammar that we could support, that led us to around a third of the functions in the date library whose contracts we could support. And at the end of this, around 3,000 call sites. So here are the overall results. And there are a lot of caveats to mention here. So this was a relatively small sample size, and it was on some code that we believed would be amenable to this kind of analysis, and only supporting a simpler subset of its contracts. Of course, we do want to rerun this kind of analysis on many more programs, wider variety of targets in future. It did show, though, that the basic approach can work and can scale to real programs. So for the roughly 3,000 call sites, we showed that we could validate statically that 95% of the calls analyzed would be in contract. 5% could not be validated. And I want to stress here that that doesn't mean there's a bug in these cases. So in fact, of those that we triaged, it was simply that they couldn't be reasoned about by CodeQL's range analysis. And potentially that could be because the code at the call site, or the values of those variables, may depend on runtime state, or state that would only be knowable at runtime, or otherwise couldn't be reasoned about by CodeQL's range analysis. And in those cases, you get a maximal range back, so int min to int max. In future, we'd like to do more to automatically categorize those cases that we can't validate. And lastly, on average, and this isn't a very scientific statistic, it took around 24 milliseconds for a check for each call site. And this was just on a modestly spec'd test machine. But the reason I mention it is just to show that this kind of approach can work, and it can be done reasonably quickly. Before I hand back to Mike to talk about future plans, one last note, which is that we did test this on some injections of intentional bugs to make sure that we can successfully find those bugs with our analysis. So to do this, we took a case that the analysis was already validating as in contract. And if you can see here, there's a call to set second. And it's not shown on the slide, but there's a contract on set second that it's the seconds that are passed in should be greater than or equal to 0. And if you can just about see the code on the right, we have a couple of test cases here where we've made those seconds negative. In the top example, it's assigned to in a conditional path. In the bottom example, it becomes negative after some iterations of a loop. So the good news is that range analysis did successfully track both of these cases, and the overall analysis detected the resulting call as a contract violation as a result. And now I'll hand back to Mike to talk about progress made since the evaluation and some future plans.
All right, so we really identified that there were two cases that were leading to the most false positives. So the first case here was just, as Peter said, unconstrained ranges. These were going to be expressions where CodeQL's range analysis didn't have any range that it could give, and so it gave from int min to int max. Specifically, CodeQL's standard range analysis does not model interprocedural analysis. So that means that if another function has a certain range, it calls this function, we don't track that. There's reasons why. For instance, we don't know if we can see every caller to f. So it's sort of a closed world versus open world assumption. Anyway, so there's some design principles that you can argue about in terms of how this should be modeled. But either way, there is not currently interprocedural range analysis, and so we don't have a constraint on the range of x before it's passed into G. That means that if G makes really any assertion about x, then it will always be raised as a potential violation, which in some cases we can look at that and see that that doesn't seem to be likely. And as a developer, if you were to see a report like this, maybe you would be tempted to fix it by adding something like this. If the function f calls the function g, then that means that the contract for g really does apply to x. You might call this contract forwarding. We want to take the contract from g and specify it here as well. And what we noticed was that standard CodeQL range analysis didn't detect this, and it didn't constrain the range of x before the function call. And it turns out that the reason why it didn't work is because, as Peter had said, BSLS assert calls into a custom violation handler. And so essentially the g of x call is reachable regardless of whether this condition is tripped or not. The conditional handler, the violation handler is not guaranteed to take an early exit. And if it doesn't exit, then G will eventually be called with any value of X. So this is something that we were able to easily extend standard range analysis to handle these kinds of cases and limit down the range. In terms of the first example, how we might solve this, it's worth talking about how CodeQL performs range analysis. So CodeQL performs range analysis by taking your program and turning it into what's called static single assignment form. Those of you who've taken compilers classes have probably heard of this. So essentially what we're going to do is we're going to take a language where a variable can be reassigned, and we're going to modify it into a new variant of that language where there is no reassignment allowed. So this variable x, first it starts at a 0, and then we plus equal param. The way that we're going to model that in SSA is that we actually create an x0 that takes the initial value. We create an x1 that takes the additive value. And then lastly, we have x2, which is what's called a phi node. And this basically, a phi node represents that we may have a value from one variable or another variable, depending on how we got there. It's really like a merge point in your program, and we can take a sort of an or of these two things. So you can see it's slightly special, and that's why it has a special name. The way that CodeQL is going to then use this static single assignment form of your program is it can say that each variable in this program has exactly one value. Because it is not reassigned, it has exactly one value. And that's part of why we have param1. Inside the if condition, we create this extra param1 value. And that's because param1 has a different range of possibilities than param0. Once we have these variables, we can track the dependencies between the variables, what calculations are performed on them in that dependency, and we can iterate over this graph of calculations in order to reach until we reach a fixed point where every variable has an assigned lower and upper bound. So when we think about this problem of how sometimes CodeQL just doesn't have a good enough range analysis, and we want to maybe categorize this stuff differently, this is what we came up with. So we added what we call provenances, lower bound and upper bound provenances, to the range analysis. So a provenance is going to represent what approach CodeQL took in order to come up with a range. And then we can filter these different provenances into different confidence categories. So we have this param0, and this is what I talked about initially, right? CodeQL doesn't currently have interprocedural range analysis. We didn't add CodeQL interprocedural range analysis to CodeQL. And so currently this is just, it is going to assume the widest possible range based on the type of param0, from int min to int max. And this is going to be a very low confidence. If we find that the violation of a contract involved a range analysis that had this very low confidence, then we can say that the overall report that contract may be violated is also low confidence. Then we have, here in this next example, we have a bounded provenance. So this is going to be the param1 variable has a bounded provenance because it is a constraint of this type range value. And we actually do track that. We track that it's a bounded type range. We track how these things relate with each other as the analysis goes on. So it's worth noting that this isn't an extremely high confidence just because we've bounded it to less than 10, because it may be sort of a catastrophic value that may never happen, or maybe it's unlikely, but maybe it's literally never going to happen. And this would, basically, I would summarize this by saying, just because we check that param0 is less than 10, doesn't mean that we know that param0 will ever hold the value 9. So it's just a medium confidence. That's going to be the upper bound of param1 is 9, and it's just a medium confidence. Lastly, we have loop conditions. And you may have wondered how loops are handled inside of SSA, given that we have a static single assignment. So the way that loops are handled in SSA is that we can have recursive phi nodes. So if we see the definition of x1 depends upon x2, and the definition of x2 depends upon the definition of x1. This is why I said earlier that when we have a graph of computations between these variables, that we can iterate this analysis to a fixed point. Once we have propagated all of these computations and we've stopped updating that propagated graph of computed values, then we're done. And this would take potentially a large number of steps. So in order to speed this process up and make this analysis more tenable, we perform what's called widening, where we basically, at every stage of analyzing a recursive phi node, we can round it to the nearest power of 2, so it takes log of n steps. And we can track when this has occurred to lower our confidence in a result just a little bit. Now, we'll talk about some future work too. First of all, our code is now open sourced. It's on GitHub. This is the link. Feel free to check it out. We are stressing that this is a proof of concept. It's a pre-release. It's definitely not a production release. It's still very experimental. We know that we have certain bugs to fix. We have bugs where there are missing constraints. There are bugs where we generate invalid SMT or incorrect SMT. Nonetheless, there's a lot of cost and a lot of value to this run, evaluate, and improve cycle. So if you take this experimental project and you run it on your code base, then you will be able to find and report and triage bugs and file them with us. That gives us information that we can use to improve the tool. We can't guarantee that we will solve those bugs, but pull requests are also welcomed. I will note as well that the documentation explains how these assertions are currently handled, and it is customizable, so you can add your own support for your own types of assertions in your program. And of course, you can reach out to me if you want help with that. So lastly, an exploration that we're currently working on that we're seeing what kind of results this will give us. If you recall the way that I described that CodeQL uses a static single assignment form of your function in order to create a graph of computations and forward those to come up with a range, this is actually something that conveniently we can try to express as SMT fairly easily. Static single assignment form is essentially a way of taking a language with mutable types, mutable variables, and pretending that it's a language with immutable variables. And of course, that's what Z3 is. Z3 has constants. So we get a very clear pathway in a lot of cases of how to translate your program directly from this SSA form into a set of SMT constraints. There is additional stuff we need to do around loops, but you can see, for instance, that we even can handle phi nodes. This x2 is equal to x0 or x1. We can know the condition that led to x0 versus x1 being the last value, and we can create the value of the phi node correctly here. So this is something where we are currently in the act of exploring it. We will see how much this improves the results. Essentially, this would allow Z3 to perform range analysis for us. And potentially Z3 would perform more advanced range analysis that would cover all sorts of interesting cases. It could understand that there's maybe a minimum and a maximum value, but maybe there's some range in the middle that can't be held. It would also potentially be able to recognize correlated ranges where the value of x is greater than the value of y, that kind of thing. And then the other thing I'll say is that once we have converted a function into static single assignment form, things like inlining become very easy. So we can potentially inline function calls that happen before the call site to try and see if you've initialized your variables to be within a correct state to satisfy the later contract. Very much experimental, but we're currently seeing if this improves things too. So the moral of the story is write contracts. Write contracts that use all of the most complicated runtime assertions that you want to add. You will already get benefit from those in your unit tests, in your fuzz testing, in your production environment if you turn them on. And all of that already has tremendous value. In addition to that, we hope that we can take your contracts as a challenge to make our tooling support your contracts. The tooling will only get better and better. I'm sure we won't be this only static analysis tool that takes a look at this problem. And we already have ideas that we're working on right now that can take it even further. So write contracts. And I think with that, we have 5 minutes for questions.
Thank you. You previously mentioned 5% of that 5% that couldn't be reasoned about, and you mentioned that at least some of that is because of dependency on runtime conditions. Now, wouldn't it be contrary to how contracts are supposed to be used, to not depend on? I mean, they're supposed to find bugs, right?
Yeah, that's true. I mean, that was one of the potential explanations here, that it was something that could be only known at runtime or just not reasoned about correctly by CodeQL's analysis. And I think it's more likely that it just couldn't be reasoned about correctly by the analysis that we have at the present time.
Yeah, I might add as well. I might add as well that with the addition of things like AI, it's possible that we'll get into a world where these noisy findings are less of a problem, and where something like finding all of these cases where we can't analyze and inserting a contract assertion, asserting a runtime check is something that can be automated. So at the moment, we don't want to bog people down with all of these sorts of alerts necessarily, but there is a world where in the future, discovering these results actually is valuable in a way that it isn't today.
So I guess I had more or less the same question, but let me maybe phrase it in a little different way to get some insight. I'm also, I guess, curious in the same way that, and maybe you can tell me if I've got sort of flip-flopped the direction you're trying to go with this, but like one way you could say is that we're trying to find places where we know a failure might happen, or a place where a failure could happen. And a place that a failure could happen might be, oh, you haven't checked the condition of the function ahead of time. Like for example, with BDLT date, you're supposed to call is valid date before you actually create the object. So if you can't guarantee that you haven't gotten to that point by the time you call date, you probably did something wrong. So does that fall into the case you were just talking about, where like maybe you just can't validate that the person has done those correct steps, or is it more just like you're trying to find the concrete paths of guaranteeing that you could have an assertion under some condition, or sorry, an assertion failure?
Yeah, I think you're right that the cases we were talking about could very well fall into the category that you mentioned. Yeah.
I know you said that you're not aiming for formal verification of the software, but I was wondering if you can see a world where maybe I could put an attribute on a function that says this analysis always fails if you can't prove this function call right here. So in our core critical security conscious functions, we can say this one must be proven to whatever extent it can be.
Yeah, I mean, I think that's an interesting idea. We definitely have, there are many projects out there that use Z3 to attempt formal verification. And so there's definitely room, if we can make our analysis smart enough to leverage that. And yeah, the tricky part there is that you'll always only ever have a subset that you want to go through that. So yeah, so something like an attribute that flags that as something specifically, I think that's a great project idea.
Hey, I have two questions. So I think the first one is, do you support disjointed ranges? And is it something that you plan to support? If not, is it something you want to support in the future?
What kind of ranges did you say?
Disjointed range.
Yeah, so the CodeQL has two standard forms of range analysis. One of them is looking for constant values, and the other one is looking for relative values. We currently only use the constant value range, so it's very possible that there could be a constraint that x is less than y, and then we only know that x is less than the lower bound of y. And so the disjoint range would be something that it wouldn't necessarily handle in all contexts. Partly this is what the SMT, the SSA to SMT compilation directly would potentially be more likely to pick up and get that for free. There is also another form of range analysis in CodeQL that, like I said, is for relative ranges, where we can track that a certain value, a certain expression has a range that's another variable's range plus a constant. And we haven't, we use that in other languages. The C++ version of it is medium done and not been super successfully applied. But the goal of that would be to better analyze things like buffer overflows. There's no reason why we couldn't, even if we don't do as heavy-handed of an SMT generation approach as I described on my last slide, there's certainly no reason why we couldn't use both range analyses to generate both constraints. And if we generated both of the constraints, then that would give an improved result in that problem. But yeah, disjointed range is going to be one of those aspects that's fundamentally trickier to validate.
Yeah, thank you. And I think my second question is, what is the advantage and disadvantage of your tool compared to existing site analysis like Facebook Infer?
I don't know what was the Facebook, what tool?
Facebook Infer, like this, is like analysis tool, and like I think they apply it pretty successfully on their very large code base. I think.
Yeah, I mean, I think there are definitely going to be other analysis tools. They're going to have their pros and cons. I haven't done that comparison myself, so I can't say. Definitely for folks who are already using CodeQL, this is a very convenient solution. And for folks who aren't, they might prefer a different tool. But that's, I think, we wanted to explore this nonetheless and see how far we could go, and we definitely want to take it further as we have the ability to do that.
Yeah, I think something like this maybe could be investigated using Infer as well. I imagine in that case you'd have to write a bit of custom OCaml, your own new sort of plugin for this kind of analysis, potentially, unless they are investigating the very same thing.
Okay, so first off, thank you for the talk. I had a question about the evaluation. So I believe you guys quoted kind of like an order of 10 milliseconds per kind of test on average. I was curious what the tail looked like on that, and if you're kind of concerned about as program sizes get bigger, especially if you go straight from like SSA to SMP, trying to kind of pick out something that'll make everything true for a big program, like what that'll look like.
Yeah, I think that's a very valid concern. Certainly the combinatorics of it could explode a little more as we're analyzing many, many more functions with contracts and many, many more call sites. I think that's where we'll have to reevaluate this in future with a more ambitious set of targets, perhaps. And yeah, I think it's definitely it's an interesting one. We can certainly do some useful analysis, and we proved that in a relatively small scale experiment. And that was really intended to give us food for thought on what are the big limitations of our current code as it stands? Like, what are the main action items for us to go and fix a whole category of false positives from that very limited evaluation? And I think once we've addressed some of those things, yes, we can absolutely try and scale this up. The other thing is performance-wise, and I mentioned it was a very unscientific test. This was a kind of minimal spec test machine that we were using. I think we may have improved on that actually in recent times, because there is now a native interface between CodeQL and Z3. And that will have helped speed things up a fair bit, because I think at the time of the evaluation, we were paying the price of a process simplification as well.
So for the evaluation, what kind of a feel for the input size on average that sort of elicited that on average 2 milliseconds, order of 10 milliseconds?
Yeah, I don't have specifics for you on that, I'm afraid. Sorry.
Yeah,
thank you.
I think the limit of the number of constraints we would be generating would be in the original evaluation would be related to the number of contracts there were, the complexity of those contracts. There probably aren't a lot of contracts where people are writing like 1,700 if conditions, and double and percented conditions. The other aspect of it would be the number of sub-objects and then the number of parameters. Basically, that's the space of how big your inputs would be, and then you'd have the space of how big the contract would be. Absolutely, one of the reasons why this SSA to SMT is an exploration and not like something we know will be good. It isn't that we don't think Z3 will give great results. It's that we don't know what the performance will be, in addition to like maintainability and things like that. And that's why it's just something we're exploring. Yeah, and there are options to do, for instance, like maybe a keep both approaches for different purposes. And unfortunately, I don't think we have the long tail numbers. I think in the original evaluation, the long tail probably would not have been significantly far off from the median. But in the work I've been doing, probably quite a lot more. I will also say that I'm in my current draft, I'm inlining all function calls up to one call of depth. I'm generating SMT for pretty much every statement in the program, even if it's not related to an assertion and things like that, on the Linux kernel. And on the whole Linux kernel with all tens of thousands of its functions, I think Z3 still solves my current SMT output in like 45 seconds. So it's pretty dang good, but we'll see how that changes as we improve it. So.
I have one more question. So do you do analysis on like the whole program as one, or like do you analyze one function at a time and like you can somehow combine the results?
Yeah, in the proof of concept, we're looking at one function at a time, one call site at a time. Yeah, and the SSA version, we look at one function definition in it. We turn the entire function definition along with its inline functions to look for contracts in those functions, et cetera, into one analysis. So one per call site in the original evaluation, once per function in the latest exploration. I also have GitHub stickers if anybody wants one. I've got Octocat stickers and Copilot stickers and stuff.
All right, I think that's all the time we have for questions. Thank you very much.
Thanks, everyone.